Alright, so hello everyone and welcome to this session. So basically, as I have already told you that I will be making more and more videos recently into the playlist, which is basically of 2 marks as well as 4 marks. So this video is about the 4 mark questions and this is the first video in the series. And guys, this videos are going to include mixed questions from the GATE as well as from the CSIR and as well as some practice questions as well. Okay, so it is going to have a mix of all the types of questions. Alright, so let's move forward and let's begin the video. Okay, so yes, so the first question is asking the correct electronic configuration for the molecular ion C2 minus is. So basically what we are having over here is, definitely guys, it's a easy question from the MOT theory, basically chemical bonding, right? It's an easy question, but it is also confusing, so it is going to require some of let's say 3-4 minutes of your time to solve this question. Okay, so what we are going to do is, I'm just going to give you some time. Just stop the video and try to do it by yourself and then we will discuss it. Okay, alright, so I think that you have tried it out by yourself. Okay everyone, so for carbon, we know that carbon is having a atomic mass less than 14 basically. So it is going to have a molecular orbital different from oxygen and much more similar to nitrogen. Okay, so we are just going to directly see the molecular orbital diagram basically. Okay, so for carbon having the valence shell electronic configuration 2s2, 2p2 like this. Also the the molecular orbit basically the Z is less than 14, and definitely we are going to see that the molecular orbitals basically formed by the combination of 2p orbitals are going to follow this pattern. Okay, alright, so this is the pattern which goes for boron, carbon as well as nitrogen, and the having definitely starts from boron because it is having a 2p orbital, right? And it is different for oxygen, fluorine and so on, right? Okay, so as we can see over here, we can just directly take the 2p2 orbital. Why? Because in the 2s2 orbital it is going to we can just fill up 2 electrons in the sigma bonding as well as sigma anti-bonding. It's very easy. So in the 2p orbitals we are having only 2 electrons like this. Okay, so for C2 it is only 2 electrons from both the sides. So definitely it is 1, 2, 3 and 4. Okay, alright. Also in the question it is asking about C2 minus. So if it is C2 minus, then definitely there is 1 electron extra. Where does that extra electron go? It goes into the sigma 2px orbital basically. Okay, so it is into the sigma 2px orbital. Now in the question the options are given, basically the electronic configuration of the orbitals is given. So I'm just directly taking from sigma 2s star, so both of them are equally filled. Then comes the pi 2py, pi 2pz, both having 2 electron, and then comes sigma 2px having only 1 electron. Okay, so this is the series. So now let's check into the options. Alright, so definitely we are going to start from 1s to 1s star as well, right? And then comes the sigma 2s2 and sigma 2s star 2. Then comes pi. So the order of the orbitals is correct. Sigma 1s, sigma 2s, and then comes the pi orbitals. But we are not having the extra electron over here, okay, into the sigma 2px, right? So we are going to just cross off option number A. Then comes option B, sigma 1s2, sigma 1s star 2, sigma 2s2, sigma 2s star 2, okay, pi 2py, which is having 2 electron, also pi 2pz, 2 electrons, also we are having sigma 2px1. So this is our correct electronic configuration for C2 minus molecule, okay, or molecular anion basically. Alright, I hope that this is clear to you guys. Also let's see the other option, sigma 1s2. Alright, okay, so this is the same as the first one, and yeah, this is incorrect. The pi star is not going to come, so definitely this is also incorrect. And yes, so here we are only talking about only 1 sigma. So this is less number of electrons than the C2 has, so definitely it is also wrong. So our correct answer is option number B. Okay, so now let's proceed with another such question. Alright guys, so we are going to proceed. Okay, so before proceeding, let me quickly tell you that I'm also an educator on the Unacademy Plus platform, and if you have visited my profile, I would suggest you to follow for regular updates about my classes and everything. Also, I would request you to visit all the special classes if it is possible. Attend the live sessions, because attending the live session is like a real experience, like sitting into a class and watching it, right? And if it is not possible, try to see the recorded videos as well, because we have solved a lot of previous year questions, and at this point when you are preparing for the GATE exam as well, it is going to help you definitely. And all of these are all of these are free to watch, and definitely everyone, all of you can attend the live session as well. But what we are having extra along with the special classes is our plus course. So basically in the plus course, we are completing the whole CSIR syllabus and helping you out in your CSIR preparation. Okay, so in the month of December, after 15th of December or 18th of December, I had started this course on preparation strategy for the next 6 months, June 2020 examination. Okay, so this was about that, and from the month of January, we are directly starting preparation for June 2020 examination. So I'm having a batch course in which I'll be taking organic chemistry. Along with that, there is also my individual courses. Okay, so in the individual course, I'll be taking and covering most of the topics from organic chemistry. So guys, my plan is to from January to March, my plan is to cover all the organic chemistry completely. And along with that, after March, basically I will be taking some important topics on inorganic as well as physical chemistry, only the selective topics which we think are going to help us out in gaining more marks in CSIR exam, right? And after, from the April itself, we are going to start studying inorganic physical, as well as we will be doing revision of all the organic as well as practice. So there is a lot of stuff which we have to provide you, and if you want to subscribe for the plus, because plus is a paid platform guys, you have to select from one month subscription, 3 month subscription, 6 month, 12 month as well as 24-month subscription basically. All right, so you have to select from those, and if you want, you can use my referral code for getting a 10% discount. So if you are using my code Jagriti S, you will be getting a 10% discount from whichever package you want to select. Okay, all right guys, so let's now focus on the other question. I hope that you will visit my profile. Okay, so the question number 2, which of the following statement is false? Okay, so it is asking about a false statement. Okay, so the LUMO for F2 molecule is an antibonding pi orbital. Okay, we will check that. A pi molecular orbital is cylindrically symmetrical around its internuclear axis. So let us see guys, we have already seen this in the last video, basically for the 2 marks, that the pi orbital, pi molecular orbital, so if it is let's assume it is talking about the bonding, because it is not mentioned pi star. So pi molecular orbital is given parity U, unjarrate. It is unjarrate because it is forming by the lateral overlap, right? So this is our pi bonding, and it is going to give, if these are the two nucleuses basically, then it is going to form a cloud above and below, but it is not cylindrically symmetrical. So one pi molecular orbital is only going to have a pi molecular cloud above and below with opposite phases, and there will be a nodal plane like this. There will be a nodal plane on the center, on the internuclear axis basically. Okay, so definitely option B is incorrect. The bond order of Cl2 species is equal to 2. Don't we know this? Cl, there is only one bond. Yes. Now, which of the following is false? It is asking. Let's see. So B is false, C is false. LUMO for F2. What is a LUMO, guys? I hope that you know what is LUMO. LUMO is lowest unoccupied molecular orbital. Okay. So if we draw the molecular orbital diagram for F2 basically, and yes guys, we know that it is having a Z greater than 14, so this is going to be if these are our 3 p orbitals, then this is going to be, I'm just roughly drawing it over here, okay? Alright, so just a second. Okay, so yeah, so it is going to be something like this, just roughly drawing. So 5 electrons in the 2p orbitals, isn't it? So 5 electrons in the 2p orbitals for fluorine. So it is going to be 2p5 of one fluorine, and this is going to be 2p5 of another fluorine. Okay, so let's fill the electron. 1, 2, 3, 4, 5, 6. How many? There must be 10. 7, 8, 9 and 10. Okay, so there are 10 electrons which are fulfilled. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So 10 coming from both the 5 and 5. Now the question is asking what is LUMO. So this must be HOMO. This is the highest occupied molecular orbital, and this is our pi star. This is our pi star, and the LUMO, which is the lowest unoccupied molecular orbital, this is sigma star. So the LUMO for F2 is an anti-bonding pi orbital, which means pi star. Is it pi star? No, because the HOMO is pi star for F2 molecule. So we can say all of them are incorrect. All of them are false. Okay. So I hope that you have stopped the video and did it by yourself. Okay. So we are going to move on to the next question. That which of the following statements is not true? Not true means again it is asking for the false statement. Okay, so O2 has small bond dissociation energy than O2 plus. Okay, we are going to check that by finding out the bond order for O2 as well as O2 plus. So guys, I would definitely suggest you to go and watch the 2 marks question video as well, because we have drawn the molecular orbital for oxygen. So what we are going to do is, I'm just directly going to write the electronic configuration of the molecular orbital of O2 as well as O2 plus. So alright guys, so what I have done is, I have already drawn the molecular orbital configuration for oxygen as well as O2 plus. So what do we see that in oxygen molecule, right, in O2 we see that the valence electrons basically are in the 2py star and 2pz star. So one electron in both of these pi star orbitals. These are our pi star orbitals. Okay, and definitely they are degenerate, that is why both of them are having one electron. Okay, now what do we have? If we are now taking out this electron, one electron, and making it O2 positive, definitely the electron is taken out from the pi star orbital, and I can remove whichever electron I want. It's going to be require same energy. Yeah, so alright, so definitely I have just removed the electron from the 2pz orbital. Okay, what now? We see that definitely guys, how to find the bond order. So to find the bond order, what we do is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So what are, just a second. Alright guys, so what are the number of bonding orbitals in oxygen? It is 2 over here, plus 2 4, and plus 2 6, plus 2 8. So I'm just going to write 8 minus plus 2, these two are in the anti-bonding, so 2 and 2 4, right, divide by 2. So this is going to be 4 divided by 2 is equals to 2. So the bond order of oxygen is 2, as we can see. Now let's find out the bond order for O2 plus. So guys, it is how much? It is 8 again, minus one of the electron is removed from the anti-bonding orbital, so it is going to be 3 divided by 2, which gives us 5 by 2, which is giving us 2.5. So definitely the bond order of O2 plus has increased, and that is why O2 has small bond dissociation energy than O2 plus. This is correct. Why is it correct? Because the bond order of O2 plus is 2.5. Greater bond order, strength, the strength of bond also increases, and higher energy is required to break that bond. So first option is correct. The vibrational frequency of O2 plus is greater than that of O2. No, because, alright, yes. So what is going to happen? The vibrational frequency of O2 plus. How do we know that? Greater, the frequency is the the value of the frequency is going to be greater. Why? Because usually see we find out the frequency of vibration in the number of wave numbers. I think that you have studied a little bit of spectroscopy. Okay, so we mostly find out the vibrational frequency in the terms of wave numbers, alright, and definitely it is given in centimeter inverse. So definitely guys, if the bond is stronger, then definitely the energy is greater energy is required for vibrations, right, and definitely it is going to have a greater vibration frequency. The bond order of O2 minus is less than that of O2. Yes, it is correct, because in the case of O2 minus, let's just write it over here only. If I am making this O2 minus, then one electron extra is added into the anti-bonding orbital, and I have to put 8 minus 5 over here, which means 3 divided by 2. So if it is 3 divided by 2, then the value would be 1.5. So the bond order is 1.5 for O2 minus, and it was 2 for O2. So definitely the bond order for O2 minus is less than that of O2. This is also correct. Yes. So the bond order of O2 plus is greater than that of O2. So let me also see this. Alright guys, so this option number D is asking about bond length of O2 plus. So definitely if the bond order of O2 plus is high, for example it is 2.5 for O2 plus, then definitely the bond length will be shorter, right? So option number D is not true. This is our false one, right? So the D is our correct answer. Alright, so here we go on our question number 4. This is our last question for this video. Which of the following compounds will have a seesaw structure? So basically guys, the question is very easy. It is only directly asking you about the structure, but it is going to take you some time if you have already not practiced this. Okay, so the question is asking about a seesaw structure. What is a seesaw structure? It has to be something like this. Okay, so let's try to find it out. So if we are talking about XeF4, so xenon is basically having how many electrons? It is completely, octet is complete, so definitely it is going to have 8 electrons. So this electron 1, 2, 3 and 4 electrons are used in forming a bond with 4 fluorine atoms. Okay, so there are 2 lone pairs which are left out. So if we want to draw XeF4, then definitely it has to be square planar, because like this the 2 unpaired electrons will be able to occupy the sp3d2 orbitals, and they are going to exist like this. So XeF4 is square planar. So we are not going to see further ones, because XeF4 in whichever option there is XeF4, we are directly going to cross that. Why? Because we have confirmed that XeF4 is square planar. It is not a seesaw. Now let's move on. XeO2F2. So again Xe is having 8 electrons. So 2 electrons are gone for bonding with fluorine. So there will be 2 fluorine attached to 2 electrons, as well as there will be oxygen. So 2 electrons again gone for oxygen. So there is 1 electron pair which is left out. So how many orbitals are required for this? So one orbital for the lone pair, 2, 3, 4 and 5. So 5 orbitals are required. And guys, when we require 5 orbitals, what is the hybridization? It is sp3d, right? sp3d, which is trigonal bipyramidal geometry. So this question is directly from B.Sc PR, or let's say including VBT. If I am talking about the hybridization, if I am including the hybridization concept, then definitely I have to say that it is from VBT as well. Okay, so I'm just going to arrange this molecule of XeO2F2 something like this. Okay, so let's say these are the pi bonds with the oxygen, both the fluorine stay axial, alright, and there is this lone pair over here. So now we can see it is looking like this, isn't it? It's looking like a seesaw, as we can see over here. So definitely this one is having a seesaw structure. What about the other one? Alright guys, so if we are talking about SeF4 basically, alright, SF4, so SF4 as well as SeF4 are going to have the same structure, because they are in the same group. Basically they are into the oxygen family. Right, so I'm just drawing the electrons for sulfur. It is having 6 valence electron, 1 for fluorine, 2 for fluorine, and there are 4 fluorines like this. So 4 orbitals required for fluorine, 1 orbital. So again there are 5 orbitals which are required in total. Okay, so 5 orbitals definitely going for TBP geometry, and definitely it is going to give us the same structure as XeO2F2 is giving. Okay, so it is also going to follow Seesaw, and both of them are in the same family. They are going to give the same structure. And let's see TeFO. So sulfur, selenium and tellurium, so this is also in the same family, and it is not going to give a completely same structure, but definitely roughly we can say, in all the other options that we are having, roughly we can say that yeah, they can give the same seesaw structure, because in the other options we are having XeF4, not at all possible. CF4, this CF4 is definitely tetrahedral in shape. Alright, so CF4 is also not going to have the seesaw structure. So our correct answer is option number C. I hope that you did this by yourself as well, and then you have checked this from my solutions. And definitely guys, if you like this video, please give it a big thumbs up, and more such videos are coming up. Please share it with your friends. Also please subscribe to the channel. And if you want to visit an academy, definitely guys, there is a lot of free content over there, and you can visit there. You can visit my profile, definitely follow for more updates and regular upcoming classes as well. Also, if you want to subscribe, then you can use this code Jagriti S for a 10% discount. Guys, never ever subscribe without using the educator's code, because you'll have to pay 10% extra. Why do you want to pay 10% extra? Okay, alright guys, thank you so much for coming, and I'll see you in the next video. Thank you so much.